Welcome to Majestic Easy World Science channel. In this video, I'll be handling magnetism. Magnetism is a fascinating phenomenon both in chemistry and in physics. So in this video, I'll be handling the chemistry and the physics aspect of it. And remember that magnetism is one aspect of electromagnetism. The second part is electricity. So magnet and electricity joined together makes up what we call electromagnetism. But I'll be handling one part today, though it becomes quite difficult to treat one part solely, but I'm going to concentrate on magnetism. Now, what is magnetism? Magnetism can be seen as a force of attraction or repulsion between two substances or between two objects or between two materials within a region that is known as the magnetic field. So in that case, magnetism have to deal with the interaction between a moving electric charge and a magnetic field. Then, for you to understand magnetism, you're supposed to know what magnetic field is. Some might call it the B field. So magnetic field is actually a region or a space within which the force, magnetic force of a magnetic material can be felt. The region or a space within a magnet that the force of attraction or repulsion can be felt. Or you can see it as a vector field. Magnetic field is a vector field that describes the influence of a magnet on a moving charge or on a moving electric current. So in that case, magnetic field is actually not visible, but the lines, the magnetic field lines, can be visible with practical, but magnetic field really exists in real sense. But we cannot see it is a kind of force being thrown off from a substance that can attract or repel another substance. So in that case, every substance on Earth actually exhibits one or two forms of magnetism. So the type of magnetism observed in a given substance depends on the atomic structure and also the type of spin observed in that particular substance. So magnetism is actually a function of the paired and unpaired electrons and the nature of the alignment of the unpaired electron of a given substance. Now, for you to understand clearly this particular topic, magnetism, both in physics and chemistry, you need to understand Pauli's exclusion principle. So you watch the video on Pauli's exclusion principle. It might take longer time to explain, but I will brief it here. You must understand Pauli's exclusion principle and understand what we call the intrinsic angular momentum, or what we call the electron spin angular momentum in physics. Remember that angular momentum is just the rotational force of a body around. So, but this time around we are talking about intrinsic spin, which is actually the spin of elementary particles or the nucleus, such as elementary particles such as an electron, also even the spin of the nucleus itself. So now, I will state the Pauli's exclusion principle. Remember, Pauli's exclusion principle told us that no two electrons in an atom will exhibit the same set of 4 quantum numbers. At least they can have the same set of 3 out of the 4, but differ in their last quantum number, which is the spin quantum number. An orbital is a region or a space within an atom where an electron is likely to be found, and a given orbital have the ability to accept or contain only 2 electrons. So, but today we are focused on such orbitals, whether they have paired or unpaired electrons. So now, because of the fact, remember that all the forms of magnetism I'll be discussing in this video are actually consequences of Pauli's exclusion principle, because Pauli summarily told us this. Even though, let's assume we have this electron 1s2 as in form of helium, which is number 2, we will put the 2 up and down, and not putting the 2 up, or spin it down. So you cannot, this according to Pauli, any of these 2 is not accepted. So this is incorrect according to Pauli. Rather, the correct thing is that one should point up like an arrow and one should point down. Because of this, we will now see why paired electrons don't have magnetic field and why unpaired electrons have magnetic field. Let's assume they are spinning in the same direction. There might be possibility of them having magnetic field. So this is it for Pauli's exclusion principle. since paired electrons spin opposite directions, that shows that their spin will also be cancelled. That is, when the electrons spin up and down in opposite direction, this is for paired orbital. Let's assume we have different sets of degenerate orbital. In this case, like in the pure orbital, which is 3, we have up, down, we have up, up. We have this maybe P, X, Py, and Pz. Checking this here, Px don't have any magnetic field because the spin, it contains it contains a paired electron. The electrons are paired, and each of the electrons are of equal magnitude but have opposite what? Spin. So because of the equal magnitude and the opposite spin of the paired electron, it cancels their magnetic field, meaning no electron here should have the ability to orbit around their own axis. That is the intrinsic angular momentum, meaning it is observed that in a real sense, I want to draw this. So this is what we mean. This is the electron here. Is observed that these electrons are actually moving even when the orbitals are no more moving within their axis. But because these two are paired, they will not be allowed to move. Therefore, orbitals with paired electrons have no magnetic field because they are of equal magnitude and they have opposite directions. But unpaired orbitals with unpaired electrons automatically have magnetic field. Why? Because they are free to rotate within their own axis, even when the orbital itself, the angular momentum of the orbital is 0. This particular electron will have the ability to orbit around their own axis. See what I mean? If you come to the structure of an atom, if you have, this is the nucleus, and we will usually have the electrons revolving around the nucleus like this. These are the electrons. So these electrons are orbiting, they are moving around this nucleus. Even when this is what we call orbital angular momentum, they are revolving. Even when this is no more moving and they stop, each of these electrons are still moving within their own axis, like this now rotating. Even when there is no translational motion, it's just like this marker I'm holding, have the ability to rotate on its own and then can now move around. Even when it's no more moving, translating, it is still on its own. If this is an electron, an unpaired electron within an orbital, it has the ability to be turning around, and that's what we call magnetic field. You see, so because it has the ability to turn around, even when the angular momentum of the orbital, that's the orbital angular momentum, is 0, meaning the orbital itself is no more moving, but the electron continuously, that's why we call it intrinsic angular momentum, or the electron spin angular momentum. Therefore, magnetism is as a result of the spinning of the inner electrons around their own axis. This time around, there shouldn't be any translation. Whether you are moving or not, intrinsic angular momentum remains constant. Do you understand that now? So, having combined this angular momentum idea and Pauli's exclusion principle, I think I've opened the door for you to understand this magnetism very, very well. Okay, now all forms of magnetism depends on the atomic structure, the Pauli's exclusion principle, and the intrinsic electron spin. That is it here, joining both the idea of physics and chemistry. So remember, this video will help you to answer many questions concerning magnetism. Okay, before I proceed, we need to know the history of magnetism. Magnets, the first natural magnet was discovered in form of lodestone, in Latin called magnetum. Some might call it magnesian stone. That's lodestone. It found in a place called Magnesia in Turkey. They gave it that name, magnetum, or in Latin. Then English turned it to magnet. So that magnet they observed was actually a form of magnetite. We will treat that when we come to forms of magnetism known as ferrimagnetism. So that lodestone, first of all, was used as a compass needle because they discovered that when you hang that lodestone, naturally occurring magnet, there is always a alignment of that stone or that magnet to the north-south position. That's the north-south position, aligning itself to the Earth's magnetic field. That makes it clear that the Earth itself has its own magnetic field. And remember that an unpaired orbital acts as an elementary magnet. Why? Because it has the ability to rotate around its axis. Since it has that ability, it can act as an elementary magnet. Okay, therefore, if you bring that lodestone, it is already a permanent magnet with a one directional alignment. It will align in the north-south direction because of the fact that like charges attract and unlike charges attract. In a magnet, there is a north pole and a southward pole. But when you bring a bar magnet, it will not write for you that this is my north and this is my south. And that's why we say magnet is always a dipole. There is no monopole magnet. It's not possible. What I mean here is that if this is a magnet as I'm holding it, and if here is my north and here is my south, if I break this into two, if I break this marker into two, I will not have only here south and here north. No. On breaking this, automatically it's polarized. Each half, I've just created two magnets. Each half will now become north, south again. See what I mean here? If we have such drawing like this, and this is a bar magnet, here is my north, here is my south. Then I decided to break this into two again. That doesn't make, immediately on breaking this into two, here is my north, here is my south again. If the same thing applicable here, when I further divide it into two, here remains my south and here is my north. So I've succeeded in creating two bar magnets. So monopole magnet is not possible.
Wait a minute, have you heard about the Majestic table? It was designed and recommended by Sir Majestic himself. Here it is. The amazing thing about the Majestic periodic table is that it provides a clear and colorful classification of elements, from P block metals to metalloids to liquid metals. It also shows the boiling and melting point of all the elements. It also has the unique feeling of electrons in the shells of each element.
To enhance the easy learning and teaching of chemistry in schools, in universities, secondary schools, in research institutes. So this Majestic periodic table, demand and special demand, as you can see that space there highlighted, that is where you can include the name of your school, or if you are dedicating it to anybody, you can write there, because you can print it to any size you like. In a Majestic size, the resolution will never be affected. So it took me about 3 months to design and provide these informations, but thank God the table is here. What made me to design this is that I discovered that these tables I see in the internet, the one I see in the market, they are not as informative as I want. And then some of them are not updated. Some still retain the fact that we have, there are like, some still see promentum as not being radioactive. Some might see them as artificial element, but it is still is a naturally occurring element, of course. So there are some modifications that this table has been made to include, and that makes it majestic.
This is super majestic.
Much practically what I mean by the poles, that monopoles doesn't exist. Over here, I think I have a bar magnet. This is a bar magnet. I'm going to pick one to explain. So, in my explanation, this one, you have this part white, the south pole, and here the red color is the north pole. It's not a must that south is white and red and north is red, though north is usually painted red, but most times you might see red and blue. But I want to show the polarity of what I mean. Here is labeled a bit, you see the south, see the north. So if I cut this at the middle here, that doesn't mean that this thing I'm holding is now south pole and here is north pole. No, if I break this particular bar magnet in the middle, automatically it will still polarize again, such that this end becomes north and this is south, the end of this becomes south and this remains north. So breaking this into two means creating two bar magnets. So monopole do not exist, probably because of the nature of the field. That's the nature of the what we call the magnetic field lines, that the B field lines, because they always form a circle and a closed loop. So, and if it arises from, if the magnetic field lines arises from one end of the bar magnet, it must close into the other end, which means it's not possible actually for one charge to exist. If something is negatively charged, something is automatically positively charged. Like in oxidation, if there must be reduction, there will be a corresponding oxidation. Like in redox reaction, if you have oxidation, there will be a corresponding reduction. If you have reduction, there will be corresponding oxidation. Then secondly, magnets can also be produced by passing it through a electric field, and passing an ion or a ferromagnetic substance through an electric field. Electric field have positive and negative charge, so it automatically shows that we must have a dipole. So there is no monopole magnet. Okay, now we want to see, let's assume this magnet is not labeled, because not every bar magnet is actually labeled. The polarity is not indicated. So if you are holding this magnet and they are all uniform colored, and then you are told to find the north and the south, normally a bar magnet, when you allow it to float, if you hang it freely, this is the one I use, you are seeing there on the screen. If you hang a bar magnet, this is a smaller one, freely on air, it will always settle at the north-south direction. That's the north-south direction. As you can see there on the screen, most times the north tilts downwards while the south pole of the magnet is upward. So even when you distort it, what I mean is that if this place I'm teaching is my north, I hang this will eventually, the north will point here, the north pole will point here. If you shake it again after everything, it will still settle down there. So in that sense, how do you test for a bar magnet? If there is anything you are suspecting, if it is actually a magnetic substance in form of a bar magnet, you just hang it freely in the air, it will settle at the north-south direction. See what I mean here? The settlement, if you hang it freely, as you can see there, it will settle in this way, mostly slant, and then it is going to, here will be the north and here will be the south. Something is here hanging it. So this is what you mean that it settles in the north-south direction. That means this part that protrudes downward most times is the north pole of the magnet, and here is the south pole of the magnet. Therefore, now we will also use this to now describe how compass works. How do compass needle works? How do you use magnet as a compass to know the locations if you are traveling, to know your north, east, west, and south, the 4 cardinal points? So the mechanism here is the same thing as the compass needle. Remember that unlike poles attract, and then like poles repel. Unlike poles attract, then like poles repel, because of the fact that the lines, the magnetic field lines are actually in opposite direction if you use the same poles. But if you use opposite poles, the magnetic field lines are actually aligning well. One pole is giving out, the other one is accepting, so there is no opposition. I will discuss that very well after teaching how this magnet works in a compass. I'll teach the magnetic field lines, the drawing and the experiment very well here. So in this case, I want to tell you how the magnet works. If you hang it this way, it will always point a bar magnet in the north-south direction, which means this particular thing now shows that this, according to my drawing here, this side is the north. Anywhere you see the magnet settle, bending this way, this should be the north part of it. Then, what I have to tell us here is that the Earth itself is a very huge magnet. Because of the fact that the Earth is also a huge magnet, that makes the magnet to always settle in north-south directions, in the sense that there is what we call the geodynamics, or what we call the dynamo effect, which believes that the Earth has a magnetic field generated by the motion of the molten ion in the outer core of the Earth. So the Earth itself is a huge magnet, just like I told you earlier, as also the orbital, atomic orbitals that have unpaired electrons, that have possibly the spin, also generates magnetic field. So the Earth is a magnet, and also as small atom is, can also act as an elementary magnet. Because of this fact, and we all know that opposite poles attract, and then like poles repel. in that case, it means that if the Earth is now a magnet, we are going to see two things. This is the magnet we are suspending on the Earth, and then let's assume this is the imaginary line of the Earth's magnet here. It automatically means, because opposite poles attract. Opposite poles attract. What I mean is, normally if I want to align this magnet, you see, it is attracting. But when I take it the same pole, that attraction will not be there. That means automatically that here the magnetic line, the Earth's magnetic field, here should be the south pole and here should be the north pole, because unlike, so that particular part of the magnet that points downwards, which is the north pole of the magnet you are holding, is equivalent to the Earth's magnetic south pole, because unlike charges attract. Then another thing is, there is what we call the geographic. We have geographic north, geographic south. So this is the Earth's. This is the Earth's magnetic field. While this is the magnet you are using, the bar magnet. Then we are talking about the Earth itself. If here, you know, is a globe, we will also have north and south. So there is what we call geographic north and geographic south. So in this case, we'll be dealing with three poles here: geographic north, and here should also be geographic south. So this implies that if you want to know the direction you are traveling, that point where the magnet bends towards shows the south pole of the Earth's magnetic field, which is equivalent to the geographic Earth north. Meaning, this north part of the magnet shows that you are traveling in the northern part. If this place points this way, it means that here is the north, and here you are traveling towards the geographic south. So that of the poles of a bar magnet or the needle in a compass rhymes exactly with the Earth's geographic poles. But the Earth's magnetic field, poles oppose each other, because this one is just what has been assumed geographically, the north and south. So if, for example, I hold this magnet now and it is hanging freely in the air here, this is already labeled. But if not labeled, if it tilts down, this should be my north. That means if I sail towards here, I'm sailing towards the Earth geographic north. That's northern part of the Earth, of course. But if I sail towards here, I'm sailing towards the Earth geographic south, which is corresponding to the south pole of the same magnet in the compass needle. But don't confuse it that this end now that is north is attracted by the Earth's south pole of the magnetic field of the Earth itself, because the Earth is also a magnet. So this is how actually the compass needle, that's the principle of the compass needle. This always confuses, but I think I've made it very, very clear. So you have three poles here: the poles of the magnetic field of the Earth, the poles of the bar magnet or the needle in the compass you are using, and then the geographic poles. So the geographic poles always rhyme with that of the magnet. What attracts is opposite poles. So if north is here, it means you are traveling towards this direction is the Earth north. You are moving northern part. So that if you're able to detect your north, it's very easy now to know your other four cardinal points and even the ordinal points. But that will be a different video altogether. If this is north, here is automatically south, and here should be the east, and here should be west. So with this, you can know the direction you are moving. Now, like I told you, this alignment and attraction and repulsion, let us see the principle of attraction and repulsion of the like and unlike poles. For us to know this first, we have to consider what we call the magnetic field lines. Magnetic field lines are lines used to visualize the magnetic field of a magnet or the magnetic field of a wire carrying current. In that case, we will see how the lines by practical, as you can see there on the screen. Practically, you can do this, and this particular plotting, that's what we call plotting of the magnetic field lines. You need iron filings and a white paper. You see that on the screen. You just bring this bar magnet, place it down, place a white paper on it, then pour the iron filings on it. There will be a line. It will align in a pattern showing you the direction. Remember that magnetic field is actually a vector, field because it has magnitude and also have what? Directions. So let us see the drawing of what you see on the screen. Remember from that screen that the magnetic field lines arises from the north pole and then converges in the south pole. So your arrow must move from north to south. It's very clear. The lines from north, it spreads everywhere, but in south it comes back. So, and that's that pattern. You can also use the plotting to know your north pole and your south pole without, if they are not indicated in your own bar magnet. Okay, so the drawing of the earth, the magnetic field lines. If you have a bar magnet, there is also the field lines for both the horseshoe magnet. The lines automatically originate from, this is north, this is south. This will be the direction of the magnetic field lines. They all move in this way, like a closed loop. The arrow must point from north to south. Then the dice moves this way. It must come in from, then from north is leaving. So over here are actually the magnetic field line, a representation. You see the arrow, it moves from north and then converges in the south pole. So I'll have to complete the arrow here. Please don't make it on the reverse. Don't do this way. If you label here north and here south, then our arrow should be correct, pointing the reverse direction of it. But according to here, north south, the arrow should be from north to south. Then there are the magnetic field lines are actually, there are some properties or their characteristics. One is that they are always enclosed in a loop. They arise from the north and then enters back from the south, comes back again. So they keep on making a closed loop. There is no end, there is no beginning, but they must start from north and go into the, so they always have a closed loop. Because of that closed loop, this also can explain why there cannot be monopole magnets, because if this magnetic field arises from here, the north, it cannot keep moving anywhere. It must come back and converge at a particular end. So if it is arriving at this end, it must enter to the next end. So if this is north, automatically the next end is the south. And remember, this also shows the strength of the magnet, because any material, any that we'll discuss further, any paramagnetic material that comes within the strength of the magnetic field will be attracted or repelled. But when you don't come within that vicinity of the magnetic field, you will not feel the effect of the magnet, the force. So this line shows the force and the directions of the force. And again, I said, why is it that monopole cannot exist? Because the magnetic field lines always form a closed loop. And then we should know it arises from the north and then converges at the south. Then the magnetic field line is always perpendicular to any the motion of a charged particle around it. These are the few things. And the magnetic field lines don't usually cross. So you can see the plottings there. When you have the two poles, the two like poles, when you have the unlike poles, you see the pattern, it is always constant that way in the plotting of the magnetic field. Okay, that is it. We now have to see, there are different forms of magnets, of course. We have the bar magnet, the horseshoe magnet, the one in U form, and also disc magnet, the one we can see in the speaker. Most times we call it the disc magnet. So these are the different forms where magnets can appear. And if they ask you what is a magnet by definition, a magnet is any object that can produce magnetic field. Very simple. That can produce what? Magnetic field. In a layman understanding, is any substance or any object that can, or any material that can attract or repel other objects. The point where the attraction or the repulsion is felt most is the poles of the magnet. Okay? So let us see the different forms of magnetism, or different types. Different forms of magnetism. taking you back a bit, I told you that the type of magnetism observed in any object or in any substance depends on actually the pattern of the atomic structure of that particular substance, the paired and unpaired electrons. So we have such forms of magnetism as diamagnetism, paramagnetism, ferromagnetism, anti-ferromagnetism, and ferrimagnetism. These are the 5 I'll be discussing in this video. So the different forms we'll be seeing are, you see these 5? Don't confuse number 5 with number 3. Number 3 is ferromagnetism, and number 5 is ferri. We have O and we have I. In this case, remember in chemistry, generally, when we say ferric substances, we refer to ion 3 compounds. We say ferric compounds, we refer to ion 3. Ferric chloride, ion 3 chloride. But if we say ferrous chloride, we refer to ion 2. But it doesn't necessarily mean that this is for ion 2 and this is for ion 3. But just listen. These are the 5 different forms of magnetism that we can observe. And I told you earlier that these are the consequences of Pauli's exclusive principle, according to the atomic world structure. Now, diamagnetic substances, or when you say diamagnetism, is just experience when a substance, the atoms that makes up a substance or that makes up a molecule are all paired. The absence of unpaired electron in a substance renders that substance diamagnetic. And that is the tendency of a substance not to be attracted by a magnetic field. Such substance don't have any magnetic field, because if you don't have any magnetic field, you will not be attracted to a magnet also. So diamagnetic substances automatically have what we call negative susceptibility. They are not attracted to magnetic field, external magnetic field, that's what I mean. Apart from the magnetic field that a substance possesses on its own, if you apply another one to that, we call it external magnetic field. So diamagnetic substances are substances that don't have unpaired orbitals or unpaired electrons. In other words, they have all paired. That is, if they don't have at least one unpaired electron, such substances are referred to as diamagnetic substances. And when you expose them to external magnetic field, they are not attracted at all. So you use the term diamagnetism. So taking a look at good examples of such diamagnetic substances are actually the so-called gold, and then copper is a diamagnetic substance automatically. So copper is diamagnetic. So copper is diamagnetic. They don't have an unpaired electron. Remember, the electronic configuration of copper is 3d10. So that d10 gives everything, makes everything paired. So that d10 makes everything paired, and that cancels the magnetic field. Remember what I told you? Just take it that when we say spin, we have minus half and plus half. If you sum up these two, for one spinning up, take it this. Then for one spinning down, you take it this way. If you sum up this, it gives you 0. So they have 0 magnetic field. And that is for diamagnetic substances. Then paramagnetic substances are substances that are attracted to external magnetic field. In other words, they are substances that have unpaired electrons. They are substances that have what? Unpaired electrons. Therefore, they are substances that at least have a magnetic field. Okay, the paramagnetic, like I told you, if you check this type of spin, they spin in opposite direction, and that makes it 0 magnetic. But in paramagnetic substances, there is no such thing. We will either have minus half or plus half, no longer minus half and, so that it will not sum it to 0. So in that case, we have, for paramagnetic substances like I defined, they are substances that have at least unpaired electrons. There must be orbitals that are not paired. At least one is enough. So if they ask you a question in exam and tell you which of the following substances exhibits paramagnetism, you look from your configuration, the one that have unpaired electron. For example, if they ask you for, although what we are talking about here is not necessarily talking about what is actually attracted to magnet. If you talk about oxygen, let's use oxygen, which is number 8. Yes, the configuration is 1s2, 2s2, and 2p4. checking this, is there any unpaired electron or paired orbital? All these, remember, S will only have one orbital. S will also have one, but P will have three. So that's the rule. S, P, D, F, you divide S into one lobe, that's one room. And remember that one block can only contain two. When that one block contains two, the electrons inside has cancelled their magnetic field. But when it contains only one, there is a magnetic field. There is what we call the magnetic moment. It's now present. Such substance now can exhibit from number 2, 3, or 4, or possibly 5, depending on. But when it is all paired, it cannot exhibit from 3 to 5. Rather, we say it is diamagnetic. Okay, so let me clean and make it clear for you. I'm using oxygen to show if oxygen atom is paramagnetic or diamagnetic. Oxygen is number 8. And the rule is S, P, D, F. You divide this into 1. P is divided into 3. And each takes 2 electrons, like I told you. Then, remember, a space or a region in an atom that can hold 2 electrons is what we call an orbital. Okay? Then D should be divided into 5. 1, 2, 3, 5. Then F should be divided into 7. We will not be considering that of F today. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Okay? We further divide. So that's it. Now, writing the electronic configuration of oxygen, we have 1s2, 2s2, 2p4. By drawing, remember, this is S. We draw one square. We spin up, spin down. Remember Pauli's exclusion principle. Don't spin up, up. Then here, we write and spin up, spin down. Then here, we will divide into 3 because it is P. We now say 1 and 3. According to Horn's rule of maximum multiplicity, both Horn's rule and Pauli's exclusion principle contributes here. You are not going to pair them like this. No. Why? Because this is still empty. Pairing cannot start until each one has gotten 1, 1. So if you are told to fill electron in degenerate orbital, this is what we call degenerate orbital. So orbitals of equal energy, we call it degenerate, or slightly equal energy. Now, since it's 4, you just give them 1, 2, 3. Give each room 1, 1, 1, 1. Even here for D, which is 5, make sure you give them all 1, 1, 1 before pairing them. So we have 4 here, we now pair. In this case, is there any unpaired orbital? Yes. 1s2, no magnetic field, 0 magnetic field. 2s2, 0 magnetic field. If we call here 2px, 2py, and 2pz, 2px has 0 magnetic field, but 2py has a magnetic field. Therefore, oxygen, if they ask you in an exam, you say it's a paramagnetic substance because it has at least an unpaired electron or an unpaired orbital. Okay, and that's the rotation of the orbital, or what is called the spinning of the electron around its axis, not the orbital this time around. It's what we call magnetic field. As it is now, it can freely move, but when they pair, they can no more move, and that cancels their magnetic field. Okay, now paramagnetic substances, iron is the most common of them. As you can see here, oxygen, it doesn't only stand for the ones you know that are easily attracted to magnet by using. So paramagnetic substances are substances that are attracted to magnets, and they are known by having an unpaired electron, and your paired electron gives them the intrinsic angular momentum, or what we call the electron spin angular momentum. Okay, then we go to the next, which is ferromagnetic substances, or what we call ferromagnetism. Ferromagnetism is just this tendency of strong attraction to external magnetic field and also becoming a permanent magnet. Substances that are attracted to magnets and can be magnetized to become a permanent magnet is what we refer to as a ferromagnetic substance. So the tendency of a substance to be strongly attracted to magnetic field and retain its magnetic alignment when the external magnetic field has been removed is what we call ferromagnetism. Those ones that can be used to produce a permanent magnet is what we refer to as ferromagnetic substances. So in other words, all ferromagnetic substances are paramagnetic, But not all paramagnetic substances are ferromagnetic. The common ferromagnetic substance we have is the cobalt, the nickel, and the iron. Iron itself is the most common. In ferromagnetism, remember, all these 2 to 5 have unpaired. It is only one that have paired. So that's why most times this might be excluded because of its zero magnetic field. These other ones might have magnetic field but behaves in a different way. Now let's discuss these ferromagnetic substances. In the what we call magnetic order, that's the magnetic system of a ferromagnetic substance, I want to show you how they are aligned. Simply put, the unpaired electrons in a ferromagnetic substances align itself in the same direction and remains that way, therefore making themselves also a magnet. So they are permanent magnets because the alignment of the unpaired electrons are in the same direction depending on the domains and the magnitude of the external magnetic field applied. So to illustrate that, let's see something in this way. I'm showing you the type of magnetic spin or the magnetic arrangement or magnetic order of ferromagnetic substances. Remember, such do not exist in diamagnetic substances. So in this case, these are the electrons. If you see this is the direction or the magnetic field of this one. All the unpaired electrons are now spinning in the same direction. So this phenomenon, any substance that is like this is exhibiting ferromagnetism. Ferromagnetism. And iron, cobalt, and nickel are the common examples of such substances. So because the arrow is showing their direction, so they spin in one direction, and that makes them polarized in a way. We now have the north and the south pole because their spin is permanent. Even though the spin, some of the ferromagnetic substances are ordinary paramagnetic at a certain temperature. And that reminds me, there are temperatures we call critical temperatures, or at that temperature there is what we call phase transition, meaning there can be transition from ferromagnetism to paramagnetism, yes. And there can also be transition from anti-ferromagnetism to paramagnetism. We will consider those transitions at a certain temperature. But look at the magnetic alignment or arrangement of the unpaired electrons in ferromagnetic substance. They are aligned in the same direction according to the direction of the external magnetic field. Remember, before attraction, there is what we call induction. If this substance should be attracted to magnet, the north pole of the magnet automatically induces south pole at this edge that is attracting it, so that this end becomes the north. If the magnet I'm holding, let me use 2 markers. If this is a magnet and the cover here is the north, and I want to use it to attract this substance. Remember, this substance is not a magnet, but a paramagnetic substance. If I place it here, this particular north pole will induce this end to become south, so that here it becomes north also. So there is an induction. That means that is the pattern of alignment, such that if it is a ordinary paramagnetic, if I remove this one will lose its magnetic property. It cannot be a magnet. But if this is a ferromagnetic substance, if I apply this external magnetic field to it, magnetizing it, that's what's called magnetization, exposing it to magnetic field. After removing this magnet, this one turns to a magnet and can now attract another thing, and that's what we call ferromagnetism. So it's a type of magnetism where the unpaired electrons are aligned in one direction such that the substance becomes a permanent magnet after the removal of the applied field, or what we call after the removal of the external magnetic field. They are actually substances that can be used to produce permanent magnets. At a certain temperature, that is when the rigidity of this alignment remains. If you hit this particular alignment, it stands like this, but at a certain temperature, it might lose it, and that's what we call the critical temperature. So it should interest you to know that at a certain temperature, ferromagnetic substances can lose their ferromagnetism and become ordinary paramagnetic. That is, if you heat a particular permanent magnet to a certain temperature, it will lose its ability to attract again and can only be attracted. There is a difference between you attracting and being attracted. Then you cannot attract, but you can be attracted to. So when substance is only attracted to external magnetic field, we call it paramagnetism. But when a substance is attracted to external magnetic field and itself attracts another magnetic substance, we use the word ferromagnetism. So there is a certain temperature at which if you heat a ferromagnetic substance, it will lose its ferromagnetic ability and turn to ordinary paramagnetic substance. Which means if this, I'm using this to hold, this is an ion and this is a magnet. I use it to hold this ion and start hitting this magnet. There will be a certain temperature I will reach. The ion will fall on its own. When the ion falls off, it means that this is now ordinary paramagnetic. It is no longer a magnet. So each ferromagnetic substance has its own temperature at which it will lose its ferromagnetism and become paramagnetic. And that temperature is what we call Curie temperature or Curie point. Curie point is actually the temperature at which, if you exceed it, at the temperature at which, when exceeded, the ferromagnetic substance turns to ordinary paramagnetic. For our example, iron has 760 degrees as is Curie temperature, named after Pierre Curie, the husband of Marie Curie, who is popular in radioactivity, actually, the husband of the first female to win a Nobel Prize. So, we'll come to that when we handle radioactivity here on this channel. Remember, you are still on with Majestic Easy World. I am here demystifying the magnetism and helping you to use them, answer questions. Please subscribe and share this video. I cannot do without you. If I'm not the candle producing the lights, I will be the mirror reflecting. And I can't play the two roles. And I thank you for visiting. If this video is helping you in any form, direct people to Majestic Easy World. We don't light a candle and put it under the bed. We bring it upward. If this video is helping you, let it help others. Thank you. Okay, so I've defined Curie temperature as one of the critical temperatures at which there will be a phase transition. At that temperature, this alignment, this is ion, if you exceed 760 degrees, this alignment will no longer be there. They will be spinning, but on a different direction. They can no longer spin in one direction. They will not be aligned. And the tendency for this to remain permanent after removal is what we call magnetization. You have changed that thing to magnet. And then ferromagnetic substances have what we call high susceptibility. High susceptibility. Susceptibility is just the measure of how much a substance can be magnetized. The measure of how much a substance can be turned to a permanent magnet. That's what we call susceptibility. Susceptibility is very high for the so-called ferromagnetic substances. And also, it is very, very high at positive value, but it is very much negative value in diamagnetic. But it's still positive in paramagnetic because it's attracted to it, but not at a high positive value. Do you understand that now? Okay. Permeability is actually the measure of the ability of a given field passing through a magnet. That's the magnetic field produced after exposing a magnet to an external magnetic field. The ease with which it allowed the external magnetic field to permeate into it, and it can now throw up more forces depending on the force applied. Do you understand? It's just like you are pushing a material. If you push 50 kg with the same force, they will not move at the same speed with when you push 100 kg with equal force. So if you expose substance A, B to equal magnetic fields, some will have more permeability, allowing the magnetic field, and some will have permeability and susceptibility goes in the same direction. If susceptibility is high, permeability will also be what? High. So ferromagnetic substances have extremely high susceptibility. Okay? We now move on to the so-called anti-ferromagnetism. In anti-ferromagnetism, the unpaired electrons are aligned in anti-parallel way. Like, this is a parallel alignment. In anti-parallel way, in other words, in opposite direction. In opposite direction. Remember, they are not unpaired. They are not paired. They are unpaired like ferromagnetic, but instead of aligning in the same direction, they align in opposite direction. And because of the fact that the alignment will involve electrons of equal magnitude and also in opposite direction, it will cancel the electric field. the magnetic field, sorry, not electric field, is opposing the normal ferromagnetism. So you see this is the magnetic order of anti-ferromagnetic substance. They spin in opposite what direction, because they are of the same side, as they have equal magnitude. The so-called unpaired electron are of the same magnitude, and they have opposite direction. They will reflect automatically what I told you will happen in diamagnetic substance, which means these particular ones, this condition is not attracted to magnet, just like diamagnetic substance. But the little difference here is that at a certain, this thing is only possible at a certain temperature, very low, at a lower temperature. The temperatures below, at low temperature, this thing will exist in this way. But at a certain temperature above another point, no longer Curie temperature now, but what we call near temperature. Remember, I've mentioned Curie point or Curie temperature, and then this time around NEEL, the near temperature. So above the near temperature, antiferromagnetic substances turn to paramagnetic, which means these have the chances of being what attracted to magnets depending on the temperature. And that reminds me what we call the Curie's law, which tells us that the susceptibility of a paramagnetic substance is proportional to the thermodynamic temperature. So all these alignments depends on the temperature, so they can undergo phase transition at a particular temperature, such that one magnetic form changes to the other magnetic form. Like I told you, the temperature above which an antiferromagnetic substance becomes ordinary paramagnetic is what we call Neal temperature. But the temperature above which ferromagnetic substances becomes ordinary paramagnetic is what we call Curie temperature. Okay? Now, we are done with antiferromagnetism. They are not attracted to magnets below that Neal temperature. But above the Neal temperature, they are attracted to what? Magnets. Okay? And they cannot be used as permanent what? Magnets in this form. Now, we move over to the next form, which is, that should be the one we call the Ferrimagnetism. Yes, I think this should be the last form of magnetism. Ferrimagnetism. In that case, ferrimagnetism, remember, don't confuse it with, okay, I'm going to clean this because I will compare it with antiferro. There is similarity in alignment, magnetic moments, in ferrimagnetism and antiferromagnetism. But the difference is that in ferrimagnetism, they are attracted to magnets and they can be converted to permanent magnets, just like ferromagnetic substances. But in antiferromagnetic substances, at that particular temperature, they cannot be attracted to magnets and they cannot be converted to permanent magnets, which means they have a very low susceptibility and low permeability for antiferro at a particular temperature. So ferrimagnetism, in this case, is a form of magnetism where we have an anti-parallel arrangement, just like here. Check the length of my arrow here. In ferrimagnetism, the unpaired electrons have opposite spin. They align in opposite direction, but they are of unequal magnitude. Like when I bring out the box in this form, we have this electron, then we have this other electron. This one up, this one down. But this one now is down, but very short. They are not of the same magnitude, which means this can freely move irrespective of this. So this one now possesses magnetic field. Unlike when they are equal, they will cancel each other if they are equal, because let's compare when they are equal. If this one tries to move this direction, this one moves this direction. And that makes the tail here to block this, and there won't be any magnetic field in this situation. So they cannot possess any intrinsic angular momentum, and that cancels it. But here, this one, even though it's positive, it can easily move within this permitted. So in ferrimagnetic substances, they have opposite spin, or their magnetic field are actually aligned in opposite direction, but they are of unequal magnitude. Unlike here, the whole arrow is expected to be equal. That's anti-ferro. But when we have bigger and smaller magnitude, we call it ferrimagnetism. And this is attracted to magnets and can become a permanent magnet. Examples of substances that have this. In fact, the first magnetic substance noticed or detected on Earth is actually a ferrimagnetic substance. Though scientists initially thought they are ferromagnetic, no. The ore of iron, which is called the lodestone, the magnetite is a good example of a substance that exhibits ferrimagnetism. When I say magnetite is an ore. Remember, this one appeared, that reminds me, this one is observed when there is a mixture of different, like a population of different ions, not of the same magnitude, like +2, that's ion 2 and ion 3, as we can see in magnetite. Magnetite is an ore of iron with the formula Fe3O4. Yes, this is actually that lodestone. But in chemistry, we can call this also magnetite. It's a naturally occurring, but this is a permanent magnet on its own. But it is not due to ferromagnetic arrangement, but rather ferrimagnetic arrangement. There is a population of, check these 3 atoms of iron here. These 3 atoms of iron, we have 2 possible oxidation states, which are +2 and +3 oxidation states. The +2 and +3 are all here. They are mixed up. That's why the +3 is the tall one, the +2 is the shorter one. And these compounds is what we also say we find them in ferrites. In case of exam, ferrites. So ferrites have this population of having +3 ion and any other +2. What is constant in ferrite is that you have a mixture of 2 cations, where one is the ion 3. And any other one can be the ion 2 or even manganese, but must have +2. So we have manganese ferrites, we have other forms of ferrites. But what matters is that there must be ion 3 there. Ferric oxide must be constant with other +2 metallic oxides. And this is where ceramics comes in. So ceramics is attracted to magnetic field, and the form of magnetism exhibited by ceramics is ferrimagnetism because of the population of charges that are of unequal magnitude with opposite spin. Exactly. So in this case, here the name of this compound is actually ion 2 diion 3. Yes, this magnetite by alphabet name is ion 2 diion 3 oxide. Ion 2 diion 3 oxide. Meaning that out of these 3 atoms, 2 have plus, watch it, 1 have +1, that's plus, 2 have +3 for ions, the charges on them. So if you sum these are 3 atoms, 1, 2, 3, but the charges are different, so there is a different population. So 2 + 3 is actually, am I correct here? 2 + 3 is 5, then 5 + 3 is 8. Yes, so the total plus here is 8. And remember, oxygen is -2. -2 times 4 is automatically -8. So that makes it cancel. Now, in this case, you have seen what I mean.
Another form is what we call spin glass. In spin glass, there is a scattered and frozen spin in different direction, not anti-parallel, but just scattered from all angles, such that you will not tell whether this can be paramagnetic or diamagnetic. Is all just scattered. And in this situation, it is unlike in the case of paramagnetic substance, where each of these are still spinning around, but rather they are frozen, they are fixed. And this type is found in some metal alloys that have a small amount of magnetic metal, about 0.1% to 10% of the magnetic metal, about just a mixture of 0.1 to 10% of magnetic metal, and the other part is the non-magnetic metal, like in the situation of mixing gold and iron. Iron is magnetic, gold is diamagnetic, as we have seen previously. So in this particular arrangement, the atoms of the magnetic element are randomly distributed through the crystal lattice of the non-magnetic elements randomly distributed. This is a random distribution. There is no particular correct order. And are they actually attracted to magnet? They are not really attracted to magnet. So this is it about another special magnetic order called spin glass. So their magnetic properties are actually complicated.
Thank you for watching. Remember to subscribe and share this video. I love you so much, but don't forget to watch the Electromagnetism joined together, where we'll see the modern day application of magnetism. If you remove magnetism, you shut down the whole city, because most of the things you use at home, motors, generators, are based on electromagnetism. So watch my video on the electromagnetism and also other educative videos. God bless you. Bye for now.